to figure out the lone pairs and the bonded pairs of electrons in a covalent compound very quickly. Under 20 seconds, as the title suggests. Slash lone pair electron. This is mostly going to be something from SSC syllabus. So, how do we usually solve these types of questions? Like, let me just pick one right now. Why isn't this by default? Which one has the most lone pair electrons? Let's say our options are. Sorry for the lame switching, by the way. I wish I could switch more. Let me try. One. Methane. Never mind, I can't do this. Methane. Two. Let's put ammonium chloride. Yeah, sure. Ammonium chloride. Third is. Let's put methane. Methane at the fourth. Let's put let's just put H2O. Okay. Now, how do we usually solve this problem? Well, to solve this problem, we have to first know what lone pairs and bond pairs are, and a covalent compound. So, let's say we got methane. We draw the structure of methane. Okay. First, there's a nucleus. There are 2 electrons. And then there are 4 electrons, because the atomic number of carbon is 6, as we all know. So 1, 2, 3, 4. Let me just fill these out. Wow. This is so useless. I'll just fill this. Ink. So that's the basic electronic configuration for the standard carbon, no isotopes or anything. Now we add the 4 hydrogens. How? In a covalent compound, each of the hydrogens share a single electron with carbon in this case. So we draw the hydrogen molecules at convection matter. These are H. So now what do we observe? At first, the electronic configuration for carbon was 1s2, 2s2, and 2p2, or 1 and 2 and 4. Now what do we know? An atom is the most stable when its outermost principal energy level or outermost orbit is fully filled up. In this case, this is K, this is L. For L, the max number of electrons is 8. Currently we have 4. So when 4 hydrogen whose individual electronic configuration is 1s1, which means it has only 1 electron, then 4 hydrogens have 4 electrons. So when these 4 hydrogens share 1 electron each with the carbon atom, then the configuration of carbon in this case becomes not 2p2 but rather 2p6, because 2 and the additional 4 is 6. So 1s2, 2s2, 2p6, which becomes 2 and 8. So the K shell is fully filled up as well as the L shell is fully filled up. Now in covalent compound, we also know that atoms share electrons rather than donating like an ion. So in this case, since they're sharing, each carbon atom also gives 1 electron each to the hydrogen. So the carbons also share 4 electrons each to the hydrogen. So this was the original. This is the original electronic configuration of a hydrogen atom. Now after sharing an extra one, this is 1, this 2, so this means K is fully filled up. So hydrogen has also assumed its most stable configuration. So enough of the basics. Now we define what a bone pair or what a bond pair is. The outermost shells of each atom in this case, like the 4 hydrogens and the carbons, the number of electrons that there are on the outermost shell, that is the number of bond pairs. Not only on the central ones, but the entire atom. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons, or 4 bond pairs. Sorry for my handwriting. So that's the absolute basics of how bond pairs or lone pairs work. For something that is a bit more complicated, since methane is like the easiest compound ever, we can try to draw ammonium chloride. First of all, the central atom is N. And if you want to know how like the central atom works, I'm also kind of ignorant about this, but as far as I know, the atom that has the most valency in the involved elements, it becomes the central atom, because since it has the most valency, it has the capability to share the most. And the one that shares the most goes into the middle. So now, there's an N, and we know that the electronic configuration of nitrogen is 1 is 2, and 2, 3, 5. So it's 2 and 5. The total is 7. Okay. Yeah, let's go. Now, we draw these. Sorry if my poor drawing skills. There's the first shell. There's the second shell. It's going to be 1, 2, 3, 4, and 5. Okay. Now what others do we have? We have 4 hydrogens and 1 chlorine. We know the valency of each of those is 1, so we go to join those. 1 on each orbit, each electron, I mean. My bad. You know what, for the chlorine, I'm just gonna draw it right now. And they scanned me. I guess now we draw the nucleuses. Say these are hydrogens. Oh, yeah, these are hydrogens, and this is a chlorine. Yeah, this is a chlorine. And what do we have here? The original configuration was 2, 5. Now, since they're sharing 5 more, then it becomes 2s2, 2p6, 3s2, 1s2. Oh my! I'm so sorry. I'm so sorry. I made a mistake. It was not 2p6. It's 2s2. 2s2 then. Oh my god, did I really? 1 is 2s2 and then 2p3. I did not know what I did with the carbon, but I'm a bad teacher. Now since we have this, we add 5 to it, then if we add 5, then 3 plus 5 is 8. But there is only 6 capacity in 2p. So we do this and we do this. Now we can argue a specific case that why did this go to 3s? Or why did this even form? Because we know that this 2 and 8, this would be the most stable configuration. So why did it even react and produce like 3s2 in the first place? To resolve that, we have to go to valence. You know, the valency of nitrogen is 3 and 5. When it has 3 valency, it becomes 1s2 plus 2. 2 in 3, then it has an additional 3, then it becomes 6. So in total, it becomes like this, which is, you're not wrong, it's the most stable configuration. I'm sorry. Yeah, this is the most stable configuration, but there's also another rule that when in SPDF, the orbital rule, whenever a sub-energy level is either half-filled or it's full-filled, then it has a really good amount of stability. In this case, since having 5 electrons attached to it satisfies that the s orbital is fully filled, then it also attains a really good stability. So in that case, it has 5 valence. Now, since we have 5 valency, the hydrogens and the chlorines also get 1 each. So as I showed earlier, the hydrogens attain 2 each and become really stable, and the chlorine, I mean, you guys probably know, but let me just see. 1 is 2, 2 is 2, 2 is 6, 3 is 2, 3 is 10, 12. This is the normal configuration of chlorine, and then if we add one more, then that's 6. This 2, 8, 8. So it's attained the configuration of neon, the one of the inert gases, and it's stable right now. So we got that, how these form, how the electronic configurations work. Now going back to let me define. I'm sorry for not drawing like the other shells of chlorine. So 1, 2, and this is 1, 2, 3, 4, 5, 6. Yeah, I mean it's bad drawing, but it works. Now, what's the bond pair and the lone pair in this? Let's start with the bond pair first. Let's start with the bond pair first. So how many electrons are there in the outer shell of all of the atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14. Okay. Yes, there are 14. And now as for the lone pairs, I'm sorry, this is all of the electrons. Now the bond pairs, this is all of the electrons. Now let's count the bond pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 bond pairs. So what are the lone pairs? The ones that have not participated in any reaction. The ones that have not participated in the reaction in the outermost shells of any atom is 1, 2, 3, 4, 5, 6. These are the outermost shells, outermost electrons of chlorine, and they have not participated in the covalent bonding. So these are only 6 in number. Now, going back to our original question, which one is the most lone pairs of electrons? We know how to do this by manually drawing, but I have to admit, this takes a lot of time. So the question is, how do we do it this fast? Because, in multiple choice exams, you won't get 5 minutes for a single question. And this is going to take you a whole lot of time to do by hand. So what the title of this video was, how to solve these under 20 seconds. I'm not lying, you can really solve this. So let's go with our original methane. We know, let's just put this here. Methane, if we do the structural bonding of this, it becomes carbon. It becomes like this. I won't bother going into detail how this works because there are probably other classes for that. And being realistic, nobody is ever going to watch this video. This is purely for my practice's sake. Now, so we drew this, the structural formula. Each of these lines represents 2 electrons. Each of these lines represents a single bond, and for a bond to be made, there has to be 2 electrons at least, and we're assuming that. So since there are 4 lines, that means there are 4 into 2 into 4, that's to 8 electrons. How do we get this again? Again, this is the number of lines, and this is the number of electrons in each bond. So the total bond pair is 2 and 4, and then we count the total valence electron of all of the atoms in the targeted compound. I can't find a better word. So what are the total valence electrons? For carbon, we know it's 2, 6, so the valence electrons is 6, and for H, the valence electron is the what do you call it? Is the electronic configuration itself, so it's 4. So the total valence electron is 10. Okay. So now, what do? We subtract the total by the bond pairs. So total valence minus bond pair is to 1. So what do we get from this? 1, 2, 3, 4, twice. Again, I made a mistake on this. This is 2, 7, 2, 4. The total is 6. Okay? So the total valence electron is 8. Total valence minus bond pair equals to 1. From this we got that the bond pair was 8. So this is 8. And the total is also 8. So this is also 8. So 8 minus 8 is 0. 0. So this is always the output. Question. My red pen is really not working. And for ammonium chloride, it's easy, we can do this again. For nitrogen, I'll just use this one. For nitrogen, the valence electron is 2, 5. So this is 5 plus. Hydrogen is 1 for each, so 4. This is plus 4. And chlorine has 7 in its outermost shell, so it's 5 plus 4 plus 7, so 9 plus 7, it's 16. We got 16. Now, we draw the structural formula of ammonium chloride, which is N is the central one because it has the most valency as we recapped. Then just put some lines, put 5 lines. Because the valency is 5, it makes 5 bonds, so obviously there is going to be 5 lines. Put 4 hydrogens and a single chlorine because their valency is 1 each, and so this is our structural formula. And now count the number of lines: 1, 2, 3, 4, 5. 5 lines, then 5 into 2 is 10. So 5 into 2 is 10. This is bond pair electrons. So we got 16 as our bond total valence electrons and 10 as our bond pair electrons. So 16 minus 10 equals to 6. There are 3 this earlier, that there are 16 total and there are 10 electrons and 10 lone pair electrons, so there are 6 lone pair electrons. Now we divide it by 2 and find the pairs, but we cannot also find pairs because it's going to be the same anyways. We find that there are 3 lone pair electrons. Oh, it's lone pair of electrons, because lone pair electrons means electrons. Lone pair of electrons means the actual pair. So now we're going to do the rest of these two very fast. Let me just erase all of this. CH3, this is hydrocarbon. So let's just draw this really quick. See, so how many? 1, 2, 3, 4, 5, 6, 7. Yes, 7. There's 7. 7 to 14 lone pair electrons, and then the total valence is 4 plus 4. 4 plus 4, and then 1, 2, 3, 4, 5, 6 plus 6, so 4. 8 plus 6, that's 14. So what do you get? 14 minus 14, because this is the total, this is the bond pair. 14 minus 14 is 0, so there are 0 lone pair electrons. This is also 0. And they can, I don't want to verify this honestly. It's too much pain. But we can check the calculations again. This is the outermost, the valence electron of C. Carbon is 4 plus 4, that's 8, then plus 1, 9, 10, 11, 12, 13, 14. And then 1, 2, 3, 4, 5, 6, 7. 72 is also 14, so it's 22. So for this is structural formula of water or hydrogen. I actually don't know what the scientific name of water is. Hydrogen dioxide. I mean, if you guys know, please inform me in the comments. This is 1, and this is 2. Then 2 and 2. This is 4 bond pair electrons. And for oxygen, we know that valence electron for oxygen is 6. This is 1. This is 1. Then 8. And 8 minus 4. This is 4 lone pair electrons, so that's 2 pairs. So this is 2, and let's verify this by just drawing it. This is oxygen, this is 1, this is 2, 4, 5, 6, 7, 1, 2, 3, 5, 6. Okay. Now we let two of them share. Just let's say just isolate one, and then just the crosses are from the sharing electrons. Now let's verify our calculations. 1, 2, 3, 4, 5, 6, 7, 8. Our total is 8. As we calculated, 8. And our bond pair is 1, 2, 3, 4, 4. As we calculated 4, so 8 minus 4. That's 4 lone pair electrons, so that's 2. This is 2, so the answer to this specific question, which one is the most lone pair electrons, is going to be 2. Ammonium chloride. I know this has been a very poor tutorial and a very poor teaching video. It's because I'm still practicing and I really hope I can do better. Thank you for watching.